at three major problems. The first problem being infant mortality. Currently, children in developing countries are 10 times more likely to die before the age of 5 than children in developed countries. Another problem being the current urine collection methods, such as catheterization or urine collection bags. They're proved to be uncomfortable, invasive, and inefficient. Another problem being the current technology out there right now that helps diagnose infants. It relies heavily on technology. So considering these three problems, we made a product that takes away these three issues, and we aim to inspire a new generation of social health innovation, and our purpose is simple. We strive to create valuable diagnostic pads that combat major health concerns.
So as Sarah said, our product provides a solution to a need. We're utilizing lateral flow in front of the diagnostic device. So that means that this is our Diaper protective pad, and it's composed of 8 layers. So you have the top protective layer. The second layer is a mesh layer, and then right after that is the reactive layer, which is where the urine is going to drop and it's going to flow to its respective region in order to indicate whether the baby has some kind of pathology with it. And so then you have layer 5, which is the mesh, layers 5 and 7, which are mesh layered, and between that is the absorbent layer, which is composed of sodium polyacrylate to ensure that no urine is flowing outside of the pad. And then the bottom layer is the support layer, which will have an adhesive on it, and that will allow the pad to be utilized in the diaper to make sure that the pad is not moving around as the baby's urinating or moving around.
So as Veronica had mentioned, one of our key components in our design are the lateral flow design of the chain. So what we decided to do was play around and optimize what best design would sort of encompass and allow for the urine to flow towards the reactive region. What we found were hydrophobic barriers were the best way to maintain the urine within the channels itself and allow it to reach the respective regions. So with this, we played around with different designs such as the squares and reactive regions and circles. And what we found were either design is works the best. And so this is an interchangeable sort of shape that will allow whatever the user intends and what would best suit the user to identify the different color changes in the region. Well, as you can see in these images above, these are drawn with crayon. And the reason that we chose crayon was the fact that crayon, a huge part of crayon is wax. And so we basically drew a design on filter paper. We melted the wax within the filter paper, so which would allow the wax to maintain the shape, and then when we drop urine within the channel, it will not surpass the filter paper itself. And so as you can see here with crayon, the problem is that it's bulky, and there's a tendency for when the wax to melt, it moves within and will suppress the urine from reaching the reactive reagents, which will then inhibit the sole purpose of our design. So then we found that wax printing was the best method for us. Essentially what wax printing is we drew something on SolidWorks. We found the design with the circles was best aesthetically for us. And we based the SolidWorks program was then we used a printer that had wax cartridges. It would print the design, and then we would melt the filter paper on a hot plate, which would then allow the hydrophobic barriers within the filter paper. And the reason with wax printing allowed us to have a cleaner shape and a more precise, effective flow towards the reactive regions.
And the reason for the divider barrier on the left-hand side, so there's 2 separate channels and then there's a divider in the center, is because we will be detecting 2 different pathologies within our path. However, this can be interchangeable dependent on if the user wants to change these. So for ours, the right-hand side is detecting nitrites, which is an indicator of urinary tract infection, and the left-hand side is detecting specific gravity on the left-hand side and pH on the right-hand side.
So we went through several tests to test our flow channels. Our first test was to test for a healthy urine to make sure we don't see any indication of nitrites or acidic pH or acidic urine. So once we dropped the urine on there, you can see that there was no color change for the indicating nitrates, and the pH turned to a blue color, which is what we expect due to the fact that the pH of urine is neutral. Then we tested for infection, and due to the presence of nitrites, we see a bright pink color change in that reactive region. And then we tested for dehydration, And due to the presence of an acidic urine, we see a yellow color change in that reactive region. And then we tested both of them together, and due to the presence of both nitrites and an acidic pH, we see a color change in both reactive regions. So through this process, we went through multiple different indicators to try to best optimize our bioassays and get a more significant color change.
So after optimizing our flow channels, we also had to go through the process of designing our pad as a complete unit. And so, as Veronica mentioned earlier, we had designed those separate layers. So within those layers, we had to kind of decide on the different amounts of things like polyacrylate, which is what is absorbing the fluid within the pad. And so by optimizing those different things, we were able to see what would provide the best coverage for the baby and less leakage. We were also able to implement a plastic layer on the bottom, which under pressure, which would be underneath the baby when it is inserted into a diaper, that it would push the fluid forward into the reactive regions. As you can see from the design on the right-hand side, there is a window cut out, and this is so that the pad can be peeled out from the diaper pad, and the color readout can be viewed from the user. So after doing this, we also had to find a means to adhere the entire pad together. We went through different methods such as gluing and sewing, and for gluing, sometimes it would interfere with the reactive regions and the chemical change, and so this would cause a false readout. And so we actually found that sewing was the best option for us. It was cleaner, it was more efficient, didn't have any interference with the reactive regions, and we also were able to do a small circular cutout for the reactive regions so that it was a better viewing for the user.
So for verification of our pad efficacy, you can see here in this video that the urine is flowing towards the reactive region. We performed several studies in order to get an average time of how long it takes for the urine to reach its respective region, and on average it takes about 26.4 seconds. In addition to that, you can see in the side view of the pad that there was no leakage, so the absorbency was proven to work with a sufficient amount of sodium polyacrylate between the two mesh layers. It won't allow for urine to flow out of the pad, which is what we want, because we want a good amount of urine from the infant to provide accurate results.
To further understand our device as a whole, we ran blind studies to understand the colorimetric efficacy of our device, the diaper detector. And this blind study told us that about 95% of our total colorimetric identification were correctly identified by the blinded users. So essentially, then we used that, calculated the specificity and sensitivity of both the nitrite detection and dehydration detection. And we found that about approximately 96% of the sensitivity and specificity were able to properly detect nitrite or without nitrite detection, while the sensitivity and specificity of dehydration was 100%. So as you can see, these percentages are very high with the colorimetric readouts.
So after proving that our pad is effective and that we were able to optimize all different things, we also were able to design or have benefits for utilization of pad in the clinics. And so our pad is essentially a low-cost solution to major health problems. And so it can also be switched out depending on what the regional needs are. So we can adapt our product and change the bioassays within those lateral flow channels to whatever we want. So there's a lot of different chemistries going on right now, a lot of new science that's coming out to develop new bioassays that have colorimetric readouts. Those can be interchangeable within our device depending on what we want to be detecting, such as bilirubin, leukocytes, and things like that. Those can all be implemented to the reactive regions. It can also, because of the design of our device, it can be split into multiple channels besides two. We can have 3-channel readouts. We can have split channels also, depending on if we want joint indicators or not. And finally, our product requires no resources whatsoever to use itself. It just requires the urine and somebody who can visually look at it and see the color change. It also doesn't require any resources. It requires little to no resources for manufacturing. So as you can see, we used sewing, we used fabrics, and we also utilized different things such as glue and crayons. So those types of things can be found in places that have a lack of resources. So as a whole, our product is inexpensive, easy to use, reliable, simple to manufacture, and very versatile.
So now that we've gone over the functionality and utility of our product, we set our sights on the market potential for our product. We essentially be entering the in vitro diagnostic market, which is projected to reach around $69 billion by 2017. And of this, urinalysis represents about 4.1%, which is about a $3 billion market opportunity. In addition to this, the International Finance Corporation has projected that within the next 10 years, spending on healthcare in sub-Saharan Africa alone is expected to double. Furthermore, the United Nations budget for children's health alone amounts to about 87 million a year. And so there's no source of funding for people that would be potentially purchasing our products. And aside from the financials, the potential impact is that about 63% of the 6.6 million children that die a year could be benefiting from our product as well. So now covering the economic feasibility, we have this chart here that just shows kind of a really mock breakdown of the material we use ourselves in lab and the cost that it would be per unit. And we came up with an amount of about 34 cents a unit, but of course this can be minimized through automated production and bulk manufacturing. And we can partner with wholesale distributors to get that out to the end users, and they can also be mass produced. So our intent is to sell in bulk so that we can maximize the accessibility to the end users. And finally, we're going to be pretty much entering a previously untapped market, because anything that's similar to our device does require a couple technology, and ours requires nothing of that sort.
Finally, the most awesome thing about our product is that it's actually novel. So the idea of integrating lateral flow channels into pattern barriers for a diaper or pattern insert is completely unique to our design, and we're the only ones who have done this in any product or any patent. So we actually have patent pending on this idea of lateral flow channels within diaper insert for your infection and expensive diagnostics. So we filed for this, and we actually have interest from Procter & Gamble. We have been communicating with them back and forth in regards to our product and intellectual property. And so we have been speaking with them as to the future of our product. And so we would actually like to just acknowledge a couple of people. Thank you all for coming, and we really appreciate everybody's help as to our product. Thank you.
You guys know that I have 3 small boys, so I very much would like to say it again. So my question was about your lateral flow assay and how it works. I think it's very clear that it's functional. It gives you very quick results. But the problem with infants is you can't always predict when they're going to go to the bathroom. You can't tell when they go to the bathroom. So what happens to your assay when it's left to sit for an hour, or when there's multiple applications of urine onto the pad?
Yeah.
How does it react?
Yeah, so the colorimetric readouts actually, they can, so for ours specifically, the ones that we have implemented in there, they are an instant change, and then the color actually stays after a couple of weeks or so. Some of them, though, however, will change, but that's only due to the fact that we only have access to certain resources based off of funding and things like that. The colorimetric assays that exist out there they do exist for that purpose. They can do long-term, long-range types of things, and that's shown in those dipstick type of things that they sell on the market. So using those chemicals into our device would work fine for that.
And I have one practical question. Where is your readout relative to the absorbent surface area? Is it on the same layer, or is it the backside?
It's on the backside. So we have that cutout windows for viewing, and so it's sealed off so that the absorbent material is in between those 2 mesh layers, and then that readout window, the color change comes out.
You can view it in our demonstration later.
I just had a quick question about the bill of materials with your existing current projections. That 34 cents per diaper, is that most of the cost in this special analysis chemicals that you'll be applying, or is it comparable to other things that are on the market? Where does it lie?
Oh yeah, so actually, contrary to what you stated, the actual chemicals themselves are the cheapest part of the product, because we're using microliters per unit to produce, so it's minimal cost for it. I think it was even less than a cent per unit from the actual amount that we're using. The bulk would be the actual materials, and that was just the estimates from what we were actually using. So we use a sheet protector for the bottom layer,